So welcome back, everybody, for today's session of the Cardiff Analysis Seminar. We are today online, and we are delighted to have Luigi Provenzano from Università Roma Sapienza from Rome, who will talk about reverse Faber-Krahn inequality for the lowest Aharonov-Bohm eigenvalue of the Neumann and Steklov problems. So Luigi, thank you very much for accepting our invitation, and over to you.
Okay, thank you, Matteo. Thank you to you for your introduction and for your kind invitation, to you and to Francesco, of course, and to the organizer of this seminar. It's a very great pleasure for me to speak here at this seminar, really. Thank you very much. So you already introduced the title of my talk, so I can start right away. And in the first part of my talk, I will resume a few facts on the magnetic Laplacian, just for maybe people who are not well acquainted with this operator. So the first part will be more or less some review part. And then I will pass to the results and to the optimization problem that we have considered. Okay, let me say that this is a joint work with Bruno Colbois from the University of Neuchâtel and Alessandro Savo, which is from Rome, from Sapienza. Okay, so I forgot, sorry. The magnetic Laplacian. Well, on R2, so we are on the Euclidean plane, at least for the moment, we consider a real one form A, which has this shape. We will call it the potential one form. I will call it in this way. And the two form given by the exterior derivative of A, which I will call B, is what we will call the magnetic field induced by this potential one form. Well, for during this talk, I will also use, with abuse of notation, the expression A to denote the vector field, which is dual to the one form A. That is the vector field given by Fg, the two components. And expression B will denote, again with this abuse of notation, the curl of A, which has this meaning in two dimensions. Okay, so it will be clear from the context if I am talking about the differential form or the vector field anyway. Okay, now for any complex valued and smooth function u, we define the one form dAu in this way: the differential of u minus iAu, or equivalently, from the say vector field's point of view, this vector field gradient A of u with this in superscript A, which is the gradient of u minus iAu. I is the imaginary unit. So we will call this the magnetic gradient of u. Okay, now I'm just setting the notation. Well, then, as for the standard Laplacian, we define the magnetic Laplacian squaring this operator. If you have A equals 0, you have the standard Laplacian, of course. More explicitly, the magnetic Laplacian can be written as standard Laplacian minus the norm of the vector field square u minus 2i, the scalar product of the gradient with A, minus iu, divergence of A. This is the explicit form of this magnetic Laplacian. And a few basic facts on this operator, which will be crucial to understand the problem and many other properties of this operator. This property is what we call gauge invariance. In fact, if we consider a smooth function phi, which is infinity and complex valued, and we consider the magnetic Laplacian with potential given by A and with potential given by A plus the gradient of phi, that is A plus an exact one form, say, then these two operators are unitarily equivalent. And this equivalence is given by this relation. And this is what we call gauge invariance. We will see the implications of this gauge invariance in a few ways, because we will be interested in the spectrum of this operator, and we will see what gauge invariance implies regarding the spectrum. Okay, and note that since phi is a smooth function, the curl, the exterior derivative of the phi, the curl of grad phi, is 0. Hence, the magnetic field induced by A and by A plus grad phi is the same, of course. So the magnetic field does not see the a change of gauge. Say. Adding this exact form is what we call a gauge transformation. So we are changing gauge. Okay. I have introduced the operator. Now I will present the kind of problem, type of problem, the family of problems that I will study. They are spectral problems, in particular the eigenvalue problem for the magnetic Laplacian with Neumann boundary condition, magnetic Neumann boundary condition. So for me, omega will be a bounded and smooth domain on over R2. The domain is a connected open set. And you see we have an eigenvalue equation, is the usual one with the magnetic Laplacian now instead of the standard Laplacian. While as boundary condition, we have the magnetic Neumann boundary condition. Instead of having grad U scalar product with the outer unit normal, we have the magnetic gradient scalar, the outer unit normal. So this is the Neumann eigenvalue problem for the magnetic Laplacian. And of course, this problem in general is understood in weak sense, in a weak formulation. We have a usual quadratic formula on the left-hand side of this variational identity, and which involves, of course, the magnetic gradient. And this variational formulation is settled in the space H1A of omega, which is what we call the magnetic Sobolev space. This space is the space of function in L2, which have a magnetic gradient in L2. Now, if the vector field is well behaved, is smooth, this space is H1 essentially. But this is not always the case. It can be a proper subspace of H1, or even for some very maybe wild potentials, it is not necessarily a subspace of H1. You can have that the magnetic gradient is in L2, but not the gradient, for example. Anyway, for the situation which we will consider specifically later in my talk, then this will be a subspace of H1, so everything is nice. But okay, if the vector field is smooth, so in very easy situation, then we have an increasing sequence of eigenvalue of finite multiplicity, which are non-negative, of course, and diverge to plus infinity. In particular, they are non-negative. It is very easy to see because lambda 1 is the minimum of the Rayleigh quotient, which is the integral of the energy over the L2 norm square of U, taken over, this minimum is taken over all function in the magnetic Sobolev space, of course. The Rayleigh quotient is positive and non-negative, hence also the minimum. So the first eigenvalue is non-negative as all the other are. You see that when A equals 0, the vector potential is 0, we have, of course, the eigenvalues of the Neumann Laplacian. But remember the gauge in the gauge equivalence. If we have the Neumann eigenvalues with one form potential, which is an exact form, or with A, which is a gradient of some smooth function phi, again, we have the eigenvalues of the Neumann Laplacian, because the two operators are unitarily equivalent. They are the same operator, just say looked from another perspective. In this case, so in the case of A equals 0, the first eigenvalue is 0, while the second one is strictly positive. You will see that during my talk, I will focus and stress often on the first eigenvalue, which will be the main object once I will finish this part, this introductory part. And in general, by gauge invariance, the eigenvalues of the magnetic Laplacian with one form potential A coincide with those when we consider a potential one form A plus an exact one form plus a gradient of some smooth function. This is the gauge invariance. Spectrally, gauge invariance implies that the eigenvalues are the same, that the spectrum is the same. So you are just looking at the operator from another point of view, say, essentially. Okay. Of course, it is natural then to consider the case in which the potential one form which we are considering is closed, but it is not exact. That is, its exterior derivative is 0, or its curl, as you think, vector field is curl is 0, but it is not the gradient of some smooth function. It's not exact, as it was in the previous case. Well, the magnetic field induced by this form is 0 clearly, it's closed by definition, but the spectrum in general does not coincide with that of the Laplacian, or maybe better, not always coincide with that of the Laplacian. And in particular, when this happens, lambda 1 is not necessarily 0. So we can have a positive first eigenvalue. Well, which is the property that determines this this difference? Well, the precise fact that discriminates when a closed one form produces the spectrum which is that of the Neumann Laplacian, or a different spectrum for which the first eigenvalue is positive, is the flux of the vector field or the potential one form around a closed curve in omega. Actually, again, around any closed curve in gamma. Let me define this flux. This flux is defined as usual. Define the flux of A around a closed curve gamma is given by 1 over 2 pi the path integral of A over a curve gamma. And then it has been clarified by Fair in 1999, but also by Shikegawa for more general Riemannian setting, that the eigenvalues of the magnetic Laplacian coincide with those of the Neumann Laplacian if and only if the potential one form is closed, and moreover the flux computed on around any closed curve in omega is an integer. So this is the precise condition that is needed to have the spectrum of the Neumann Laplacian. So in particular, it's just one loop. If you find inside your domain a loop for which the flux is not integer, then the spectrum does not coincide. In particular, lambda 1 is strictly positive. You have strictly positive lambda 1. Then in a sense, there is a whole space of differential one form which are closed but not exact. So they are in between the closed and the exact one form, which we can still say gauge away. So the and for which then the magnetic Laplacian has the same spectrum as the Neumann Laplacian for the without magnetic fields. So there is this class of one form, of closed one forms. But now we are interested in one form, in potential one form, for which the spectrum, of course, is not that of the Neumann Laplacian, for because okay, we want to study this situation, not the Laplacian standard Laplacian situation. And to clarify better this this fact, the fact that I just told you right now, I want to present a simple case, a one-dimensional case. Up to now, I said that we are working two dimension, but to explain this theorem over Fair and this fact of the flux integer non-integer, let me present a one-dimensional situation which really clarifies the situation. Of course, let me mention, and this one-dimensional toy model is the magnetic Laplacian on the circle. So before starting, let me just say that the magnetic Laplacian is defined in a natural way also on domains of Riemannian surfaces or compact Riemannian surfaces, and we will come back later on that. But this is just to introduce the fact that we can define it, for example, on a one-dimensional manifold that is the circle, the closed circle of length 2 pi, the boundary of the unit disk. You can imagine. Then we can consider the one form. Now we are in one dimension, A, given by nu dt. Nu is a number, it's a real number. T is the arc length parameter of the circle, so everything is quite clear. This one form is clearly closed, it is not exact, and the flux around the unique closed curve that you have in the circle is nu. So the flux is nu. Well, write the magnetic eigenvalue problem on the unit circle. It's explicit. It is minus u double prime in arc length variable t minus u double prime plus 2i nu u prime plus nu square u equal lambda u. We don't have boundary conditions because we are on the circle. This means periodic boundary conditions, let's say. So the problem is quite easy to solve, and you see that the eigenvalues are given by the set of numbers k minus nu to the power 2, where k ranges in the integers. And the corresponding eigenfunction are the e to the I, kt. T is the arc length variable. In particular, the first eigenvalue is the minimum of all these numbers when k ranges in z. And you immediately see that this first eigenvalue is not 0 unless nu is in z, is an integer. If nu is an integer, then the spectrum you can see is exactly the spectrum of the Laplacian on the circle, that is the spectrum of minus u double prime, of course. while it is not that if nu is not an integer. So here in this toy model, you really see what is happening. For example, if you let nu to be a number between 0 and 1/2, then lambda1 is just nu squared, just to see which form takes the first eigenvalue. So if nu is 0 because in this case the spectrum is the usual spectrum. Okay, here you really see what is happening. Okay, after this explanation on a simple situation, we go back to R2, to our plane. So from now on, we are trying to focus on a class of potential one forms which are close and not exact, and which have flux nu in around any curve containing at least a pole. The Aharonov-Bohm time potential. So I will consider the magnetic Laplacian with potential one form of the following type, of the Aharonov-Bohm type. How are they defined? I am sorry for these formulas, but it's really easy to understand. A bit of notation. X for me is a point in R2 with coordinate x1, x2, and we fix a distinguished point, which is x0 with coordinate x01, x02, which we will call the pole of the potential, and we fix also a real number nu. So first we define this one form x0, defined as minus x2 minus x20 over the distance to x0 square, the x1, plus x1 minus x10 over the distance to x0 square, the x2. And then the potential one form which we will consider will be nu times the one form that I have just defined. To fix the ideas, if the pole is the origin, is 0, 0, then the potential one form which you consider is nu times minus x2 over norm of x squared, the x1, plus x1 over norm of x squared, the x2. So it is a very well-known one form. Is close, not exact, in any region containing the origin or the pole. A few properties to recall what this one form, how this one form behaves. It is closed, so it induces that zero magnetic field, of course. RT for me here and through all the talk denote the standard polar coordinates in R2 centered at the pole. R is the radial coordinate, which is the distance to x0. T is the angular coordinate, which ranges from 0 to 2 pi. Well, in this system of coordinates, this potential one form just reads nu dt. It's just that. What is the flux of this potential one form? Well, the flux of this potential one form around any closed curve which contains the pole is equal to nu. So the flux does not depend on the path, but it is nu if it contains x0. Of course, if the closed curve does not contain x0, this form is exact because 0 is the singularity. And then finally, I state after some time, after 18 minutes, the problem which I will consider is the Neumann problem for the magnetic Laplacian with Aharonov-Bohm potential with pole x0 and flux nu. This is the problem which I want to consider. And what kind of problem I want to consider for this problem? Some optimization problem for the first eigenvalue. Let me just comment a few things on the spectrum. Again, this problem admits an increasing sequence of non-negative eigenvalues of finite multiplicity. Lambda1 is given as usual as the minimum of the Rayleigh quotient in the magnetic Sobolev space. You note that the vector potential here is not smooth on R2. It's smooth on R2 minus x0, but this is not a problem, of course. And in this case, the magnetic Sobolev space is a proper subspace of H1, and it can be identified as the subspace of H1 of those functions in H1, of course, but such that U over the distance to x0 belong to L2. So we are requiring some higher integrability near the pole x0, of course, where there is the singularity of the potential. So it is a proper subspace of H1. Well, now, how the spectrum of this operator what is the shape of the spectrum of this operator? So if x0 belongs to the domain or x0 belongs to some bounded connected component of the complement that is some whole, picture are coming in a slide, then the first eigenvalue is strictly positive if and only if the flux is not an integer. On the other hand, if x0, the pole, belongs to the unbounded connected component of the complement of omega, or in any case, if the flux is an integer, then the spectrum coincides with the usual Neumann spectrum of the Laplacian, and in particular, lambda 1 is 0. I skip this because maybe I want to stay in time. This can be deduced by the result of welfare, even if in this case, in the Aharonov-Bohm case, there is even a simpler and more intuitive explanation for this, and this is related to the example in the circle that I gave to you, but I skip, it's not important for now. And let me show the picture. First situation, x0 is inside the domain. If the flux is not integer, lambda 1 is strictly positive, and the spectrum is not that of the Laplacian. If nu is an integer, then the spectrum is that of the Laplacian, and lambda 1 is 0, of course. But also, if x0 is here, is inside some hole, some bounded connected component of the complement of omega, the first eigenvalue is positive when the flux is not integer. Of course, if the flux is integer, we have the spectrum of the Laplacian. And here, in this case, in any case, for any value of nu, here we have that the spectrum coincides with the spectrum of the Laplacian. If the pole is outside the domain, in the sense that it's really outside, the spectrum coincides with that of the Laplacian. Okay, and as I was anticipating, we are interested in this shape optimization problem. Maximize lambda 1, so the first eigenvalue, among all bounded domains with fixed measure, with fixed area, since we are in R2. So look, this is a maximization problem for the first eigenvalue, which in general is positive, if the flux is not integer, of course. The minimization problem is trivial because the minimum is 0, and you can imagine that is attained when the pole is in the unbounded component of the complement, for example, or on the boundary, whatever. So the maximization problem is the relevant problem here, and it is for the first eigenvalue. So I recall to you the two main well-known results for the standard Laplacian. The Faber-Krahn inequality. The Faber-Krahn inequality is an isoperimetric inequality for the first eigenvalue of the Dirichlet problem. So I'm denoting here with lambda 1, lambda k, the Neumann eigenvalue. So lambda 1d is the Dirichlet one, but it appears only here, which states that among all bound domains of fixed measure in any dimension here, the ball with the same volume, omega star, minimizes the first Dirichlet eigenvalue. So it is an inequality for the first eigenvalue. For the Neumann Laplacian, we have the Zegov-Weinberger inequality that says that among all bounded domains of fixed measure, the ball with the same measure maximizes the second Neumann eigenvalue. So lambda 2 here, the second Neumann eigenvalue of the Laplacian, because the first Neumann eigenvalue of the Laplacian is 0. And why I call the result for the magnetic Laplacian reverse Faber-Krahn, because, okay, it goes in the opposite direction with respect to the Faber-Krahn, because it is a maximization problem, but it is for the first eigenvalue. So one can argue that it can also be called the Zegov-Weinberger for the first, but anyway, question of names, say. Let me just stress the fact that our optimization problem is for the first eigenvalue which is positive in general. Okay, from now on, we shall assume, of course, that nu is not an integer, because otherwise lambda 1 is 0, and is always 0, and we have nothing to tell. And again, by gauge invariance, we can always restrict to the case nu in between 0 and 1/2. So by gauge invariance, we can always fall in this situation, in this case. So nu will be between 0 and 1/2 for me. And this is the main theorem of maybe the talk. which is for planar domains. I state it like that now, then we will see some generalization. Well, let me state this theorem. So we have a smooth and bounding domain in R2. A, the Aharonov-Bohm potential with pole x0 and flux nu, and B, be the disk centered at x0 with the same measure, the same area as omega. Then lambda 1 of omega is less or equal than lambda 1 of B. And the equality holds if and only if omega is equal B. B, I recall, is the ball centered at the pole, because it is important. Now, this problem is not translation invariant, of course. So the ball centered at the pole of the magnetic potential is the unique maximizer. Okay, let me comment a few. I don't enter in many details, but let me comment a few a bit the strategy of the proof, because actually, in order to prove this this theorem, we had to prove a reverse Faber-Krahn inequality for a Schrödinger operator, for a more general Schrödinger operator. But let me get to that. Well, we are trying to find an upper bound for lambda 1, an upper bound which we want to be in terms of lambda 1 of B, of the disk center at the pole. Usually, when looking for upper bounds, we use the min-max principle. We know that lambda 1 of omega is less or equal than the Rayleigh quotient computed on any test function u in the space. So one should find an appropriate test function, the right test function to identify the maximum, say. We will see that the right choice of a test function will be given by a first eigenfunction of the disk centered at x0 suitably extended to R2. But before getting to that, note this thing. If we test inside the Rayleigh quotient a function u which is real, we see, and these are explicit computation, that the magnetic energy takes this form. The integral of the magnetic energy takes this form. Is the integral of the grad u square plus something, the norm of a square u square, which looks like the energy associated with the Schrödinger operator, of course, with potential norm of a square. So, in particular, this tells that the first eigenvalue of the magnetic Laplacian is always bounded above by the first eigenvalue of a Schrödinger operators minus Laplacian plus V, where V is potential given by a real potential given by the norm square of A of the Aharonov-Bohm one form, say. This is easy, just test, instead of testing over all complex valued function, you test only on real valued function and you obtain that. In particular, you always have this. The first Aharonov-Bohm eigenvalue is less or equal than the first eigenvalue of a Schrödinger operator with this real potential given by the norm square of A. And the equality holds if and only if there exists a first eigenfunction, Aharonov-Bohm eigenfunction, which is real. And in this case, it is also a first eigenfunction of the Schrödinger operator. However, the first eigenfunction for the Aharonov-Bohm magnetic Laplacian is real only in very few cases. It is real only if the domain is a ball or is an annulus centered at the pole. So it is very rigid to ask that an Aharonov-Bohm eigenfunction is real. So we have not many choices. Then we are reduced to the study of a reverse Faber-Krahn inequality for a Schrödinger operator. Why that? Because we know this inequality. First eigenvalue of Aharonov-Bohm less or equal than first eigenvalue of this Schrödinger operator. Now, if we are able to prove that the first Schrödinger eigenvalue is less or equal than the first Schrödinger eigenvalue on the disk, we are done. Because in the case of the disk, the first Schrödinger operator with that potential is exactly equal to the first Aharonov-Bohm eigenvalue on the disk. So we are recast to studying a reverse Faber-Krahn inequality for a Schrödinger operator of this form. And then let me state this side result, which holds in any dimension and for more general potentials. So now I'm considering a Schrödinger operator. V is a non-negative potential, which is radial with respect to a pole, x0. So I will denote it as V of r. So it is a function of the variable r. R is the distance to x0. We consider the first eigenvalue of the associated Schrödinger operator. And the potential which we consider in general can also be singular at x0. We are interested in this minimum, and if the and for example, when V comes from the Aharonov-Bohm potential one form, V is nu square over R square, which is singular at in 0 at x0. Nevertheless, this Schrödinger operator admits a discrete spectrum, so it is not a problem. So let me state the theorem. Now, again, we are speaking of, about the first eigenvalue of a Schrödinger operator for domains in Rn. And under three assumptions, we have a reverse Faber-Krahn inequality. The assumptions are quite natural. They may seem involved, but they are very natural. In many concrete situations, we will see they are very easy. They translate in very easy formulas. First assumption, the first eigenfunction of the Schrödinger operator on the disk is non-negative, non-decreasing, and radial. That is, we can find a first eigenfunction of the Schrödinger operator on the ball which is radial, increasing, and positive. Then we assume also that the potential is radial with respect to x0. It is non-negative, already said, and decreasing in the radial direction. Third assumption, this strange differential inequality, which we will see, it is very natural. It translates in very natural stuff for some concrete situation. V prime plus 2 v square r less or equal than 0. Well, under these three assumptions on the potential, we have that the lambda 1 of omega is less or equal than lambda 1 of the disk of the same area centered at x0. So we have, under these three assumptions, that the reverse Faber-Krahn inequality holds for this kind of Schrödinger operators. And for this, actually, I want to give, say, a rapid look at the proof, because this is the core of the proof also for the Aharonov-Bohm at the end, but it is really easy, and it will follow by a picture in the next slide. So we take a first eigenfunction of the Schrödinger operator on the ball, by assumption it is radial, non-negative, and non-decreasing, and we extend it constantly to Rn. So it is u of r inside the ball. It is radial, so a function of one variable. U of and takes the value u of capital R, which is the radius of the ball outside. And from the min-max principle, what do we have? That the first eigenvalue of omega is less or equal than the Rayleigh quotient computed on this test function. Now, the isoperimetric inequalities provide if we can upper bound this Rayleigh quotient by the same Rayleigh quotient where the integral are on the ball, because in that case, this is exactly lambda 1 of the ball. Now you see that the integrands, the function integrands at the numerator and the denominator are radial functions. Well, now, if the radial function in the numerator is radially decreasing and the one in the denominator is radially increasing, we are done. The proof is just this picture. With f of r, I just denoted the integrand of the numerator, which is a radial function. If the integrand is decreasing, say non-increasing, and the denominator is non-decreasing, this picture, just analyzing this picture, you see that this Rayleigh quotient is upper bounded by the same quantity on the ball, because these regions in blue and in red have the same measure. So the numerator, the value of the function here, here, and here is less than 1 than the integral of the same function in the red spots, and vice versa for the denominator. It's just that, so it's simple observation. We conclude then, this proves the reverse Faber-Krahn for the Schrödinger operator. We conclude the proof for the Aharonov-Bohm case. In this case, we have the potential which comes from the Aharonov-Bohm potential one form is nu square over r square. It is radial and radially decreasing. We can compute the first eigenfunction of the Schrödinger operator on the ball, which is also a first eigenfunction of the Aharonov-Bohm magnetic Laplacian, which in this case is real and radial, and is given by a Bessel function of order nu. This is, everything is quite explicit, so it can be chosen real, radial, and radially increasing. Also, the third assumption is easily checked. And then we conclude lambda 1 of omega, the magnetic Laplacian, less or equal than lambda 1 of the Schrödinger operator with this potential. Then for that we have the reverse Faber-Krahn. So this is less or equal than lambda1 of the disk for the Schrödinger operator, but this is exactly lambda1 of the Aharonov-Bohm magnetic Laplacian, because in this case, the two coincide. And this is just the proof. So this concludes the proof. This is the only, say, main proof that I wanted to show you today. And I can go on. Are there any questions at this point or not? Can I proceed to some further, say, extensions of the result?
Julian has a question.
Yes. Yes.
I would like to ask about the equality case. So if you have equality, how do you get that the thing is a ball?
Yeah, because actually all this stuff, all the inequalities here, f non-increasing, u square non-decreasing, are strict. These are strict inequalities. So that in that case, you get the equality thing. And moreover, there is another thing. And I said that, let me, where I was. Okay, here also, maybe there are several reasons. You have this equality here happens only if the domain, the equality between the eigenvalue of the Schrödinger operator and the Aharonov-Bohm operator can happen only if the domain is a ball or is an annulus. And because this is a kind of rigidity, I can explain you later, given by the Aharonov-Bohm type potentials. You cannot have real eigenfunctions on any other domain that is not radially symmetric around the origin. So, okay.
Thank you.
But it's, yes, Matteo, you had.
I don't know. Julian had one. So
okay. Sorry. Okay. Now, actually, what I showed you now for planar domains, for domains in the Euclidean plane, is just, as we shall see, a corollary of a more general result, which holds for manifolds of revolution. I will not give the details of the proof here, but I want to describe the results. First of all, the reverse Faber-Krahn inequality for the Schrödinger operator can be extended to more general Riemannian manifolds of revolutions around the pole x0 of any dimension, say. Just condition 3, the first two conditions are the same. Condition 3 has just to be replaced by this one. V is the potential, and theta prime, theta, what are these functions? Theta is the density of the Riemannian metric in polar coordinates around x0. We will see in a slide what is this density for people that do not know. For in the case of the Euclidean plane, theta is just r, the radial coordinate. So, without entering into the details, what we have a reverse Faber-Krahn inequality for a Schrödinger operator on manifolds of revolution around the pole, holding under suitable assumptions, 1, 2, and 3, suitably written for this context. Well, but in this setting, and in dimension 2, what is the magnetic Laplacian with Aharonov-Bohm potential one form? Well, there is a natural way to define it. On a manifold of revolution around the pole, of course, we have the normal coordinate system, or polar coordinates, if you want, RT, as usual, the pole x0, and we define the potential one form in this way, nu de t. This is the natural definition of a potential one form, which we will call Aharonov-Bohm potential one form. This is closed and has flux nu around x0, around any curve containing x0. Well, in polar coordinates, what is the norm square of the potential one form? Is nu square over theta of r square. Again, what is this theta of r? Some standard situation. Theta of r is r for the Euclidean space. Hyperbolic sinus for the standard hyperbolic space of curvature -1. Sinus for the standard sphere of curvature 1. So when you write integral, for example, in polar coordinates around the point, this theta of r is the coefficient that enters in your integral, is your weight, of course. It is r when you write integrals in polar coordinates in R2, of course. The other situation is sinus, hyperbolic sinus, and sinus, for example. Well, if we exploit for the Schrödinger operator on a manifold of revolution with a density theta and with potential nu square over theta of r square, condition 1, 2, and 3, they really take a very simple form, which is a condition, which are two conditions only on the density. If you remember, for example, condition 1 asked for the existence of an eigenfunction on the disk, which is increasing and positive. Actually, in this situation, this can be reduced to a condition on the density, because that depends only on the density. Okay, so our condition for the validity of the Schrödinger, the reverse Faber-Krahn for the Schrödinger operator, are conditions only on the density of the metric in polar coordinates. And these two conditions provide a large class of manifolds of revolution for which the reverse Faber-Krahn inequality holds for the Schrödinger operator, and also, of course, for the Aharonov-Bohm magnetic Laplacian. A family of this kind of manifolds is given by R2 with G. G is a complete rotational invariant metric around x0. So R2 with a rotational invariant metric. In this case, the Gaussian curvature is defined, can be computed and is given by minus theta double prime over theta. We have the normalization, we consider the normalization theta prime of 0 equal 1. Then you see that the two conditions are satisfied in this case always when k is less or equal than 0. What does it mean? That if we have a smooth and bounded domain in a manifold of revolution with pole x0 and with non-positive Gaussian curvature, and we consider the first eigenvalue of the Aharonov-Bohm magnetic Laplacian with pole x0 on omega, then lambda 1 of omega is less or equal than lambda 1 of the disk of the same measure area centered at x0, equality if and only if omega is equal to b. So this reverse Faber-Krahn holds for any manifolds of revolution around the pole. Note that this statement is slightly different from the one before, because we have a manifold of revolution around a pole, and we are considering the magnetic Laplacian with pole exactly at the pole of the manifold of revolution. But of course, when we are in R2 or in H2, any point is the pole of this map, because these are manifolds of revolution around any point. Then, as a corollary, we have the same result, which I stated to you in the first part of my talk for R2, which can be stated exactly in the same way for H2, for the standard hyperbolic space. So we have the reverse Faber-Krahn inequality in these two settings. Now, conditions 1 and 2 can be applied also in the case of the sphere. It is not a manifold of non-positive curvature, but you can use condition 1 and 2 as before. But direct application of these two conditions provides that the reverse Faber-Krahn inequality is true on the sphere only if we suppose that the domain is contained in a spherical cap of radius pi over 3 around x0. And this is somehow restrictive. It's not really nice. We want to get at least to pi over 2, which is more natural. In fact, with some additional work, which is specific for the case of the sphere, we can get to pi over 2. This means that, now I don't repeat all the statements, this means that essentially the reverse Faber-Krahn inequality holds for all domains in the sphere which are contained in a hemisphere centered at the pole of the magnetic potential. So the proof is in the spirit of Weinberger, and especially of the Weinberger's inequality for the second Neumann eigenvalue on the hemisphere proved by Eschbo and Ben-Gurion. However, if we try to prove the result taking the Zigo points of view, we can improve the result in the sense that we can extend to another class of domains. In fact, we can prove that the reverse Faber-Krahn inequality holds for simply connected domains in the sphere, which have measure area not exceeding 2 pi. So with measure not greater than 2 pi, not greater than the one of the hemisphere, and this is reasonable. So this theorem says that it is not needed that the domain is contained in some hemisphere, but that its measure is less than the one of the hemisphere, and that is simply connected. And this is the Zigo point of view. Other fun, say, consequences are for problems of optimal placement of the pole. If you consider a disk in R2, H2, or in the hemisphere, and you want to place in an optimal way the pole of the Aharonov-Bohm potential inside the disk in order to maximize lambda1, well, the way to do that is to place the pole at the center of the disk, of course. And to prove this for S2 plus, we need the result for simply connected domains done in the Zego spirit, say. Okay, this will have other consequences, but I won't talk about. Very rapidly, I end with the Steklov problem, where where really I have only to state the results. So, what is the Steklov eigenvalue problem? It's this one. We look for functions such that the magnetic Laplacian of u is 0, and the magnetic normal derivative is equal sigma u. Now, sigma is the eigenvalue and appears in the boundary conditions. Ax0 nu is the usual Aharonov-Bohm potential. Again, we have the usual sequence of non-negative eigenvalues, and if the flux is not an integer, sigma 1 is strictly positive. Or if x0, of course, is not in the unbounded connected component. Now, again, by gauge invariance, we will always assume that nu is in 0, 1/2. And here, just to give you a flavor of how is the spectrum, here everything is quite explicitly computable. In fact, for the disk centered at x0, the eigenvalues are given by k minus nu, where k ranges into the integers, and the eigenfunction are r to the power k minus nu, e to the power ikt. In particular, the first eigenvalue is nu, the eigenfunction is r to the power nu, r is the radial variable. So the first eigenfunction is radial, positive, can be chosen positive, and radially increasing. Everything is quite explicit, and again, the arguments used for the reverse Faber-Krahn for the non-linear problem hold, of course. And then we have the reverse Faber-Krahn for the Steklov problem. Everything is the same. So sigma 1 of a domain is less or equal than sigma 1 of the disk with the same area centered at x0. In this case, this eigenvalue is also explicit, square root of pi over the measure times nu. Equality again, if and only if omega is equal to b. The analogous result for the standard Laplacian and for sigma 2, of course, is the well-known Brock's inequality. And this is a problem of maximization under measure, area, or volume, as you wish, constraint. But for the Steklov problem, we can consider also the maximization problem under perimeter constraint. In the case of the standard Laplacian, this is the well-known Weierstrass inequality that says that among all bounded, simply connected planar domains with fixed perimeter, so the boundary measure, the ball is the disk, is the unique maximizer. This is true only on the plane. And this is for the second eigenvalue, because the first one is 0 for the Laplacian, of course. And we have the analogous result for our first, say, eigenvalue, which is positive in this case. Namely, for all simply connected domains on the plane, the disk centered at x0 with the same measure is the unique maximizer. So this is an isoperimetric inequality under perimeter constraint, which holds for simply connected domains, as in the case of the standard Laplacian for sigma 2. Equality again, if and only if omega is equal to b. This is, say, the last thing, and then maybe a few final comments on future perspective. Of course, to prove Weierstrass inequality, we cannot use the techniques used for the reverse Faber-Krahn. The strategy is completely different, but just 4 points here, not anything complicated. How to do that? You can consider a biolomorphic map which maps omega into the unit disk and which fixes x0. We can consider x0 inside the domain, which is simply connected. Otherwise, sigma 1 is 0. Now, if A is the Aharonov-Bohm potential on B, I remove the subscript, with pole x0 and flux nu, on omega, instead, we consider the magnetic Laplacian with potential phi star A, the pullback of the potential A. But now A and phi star A are both closed, have the same flux, and by gauge invariance, they have equal first eigenvalue. Then we study the eigenvalue of omega with this potential phi star A. And we use the min-max principle for this. Sigma 1 on omega with phi star A is less or equal then the Rayleigh quotient computed on a test function. What do we use as test function? We use the pullback of the eigenfunction on the unit disk of r to the power nu. How we conclude? Well, this test function is equal to 1 on the boundary because it was 1 on the boundary of the ball. So at the denominator, we have just the measure of the boundary. And at the numerator, we have just that the magnetic energy is conformally invariant, which is another thing that we prove is. That means that the integral on omega of this energy is equal of the integral over the unit disk of its magnetic energy. And this is just the first eigenvalue times the length of the boundary. And this concludes the proof. Okay. Maybe, I don't know if I have time for a remark. Just, I tell you just the first one, which is maybe an anticipation of some questions. So what happens for lambda 2 and sigma 2, the second eigenvalue in this case, of course, because we have studied the first one, but the standard isoperimetric inequality for the Neumann Laplacian are for lambda 2 and sigma 2 for the second eigenvalues. Well, first fact, lambda 2 for the disk centered at x0 is always less or equal than lambda 2 of the Neumann problem, so without magnetic potential, which we may think of an eigenvalue for the magnetic Laplacian when the pole is outside. So here, lambda 2 of the Neumann problem is greater than lambda 2 of the disk where the pole is in the center. So one may argue, okay, maybe lambda 2 of the Neumann problem realizes the maximum among all. Fact 2, we can find a disjoint union of two disks on which one has the pole in its center, and for which the second eigenvalue is strictly greater than the second Neumann eigenvalue. So it is not the second Neumann eigenvalue of the Laplacian, the maximizer. So what is the maximizer for the second one? Is one of these disjoint union or disks with one having the pole inside. And the same facts are true also for the Steklov problem. So, and other questions remain open. Other direction are to study Aharonov-Bohm eigenvalues for domains in R3. Now here you don't have a pole, of course, but we have maybe a line or a curve, singularities, or on surfaces, and consider other potential one form, like this one. This one gives rise to a constant magnetic field B/2. This problem has a very different nature from the Aharonov-Bohm one, and it is really much harder. Okay, and I believe I finish here. And here, this is the preprint. It's recently appeared in the archive. And thank you for your attention. I went a bit long, sorry.
Oh, perfectly fine. Thank you very much.
Thank you.
So, questions for Luigi?
Could I ask a naive question, which is not actually strictly about your work, but it came to my mind when you were mentioning, I think, the result of Elfer. So suppose you take a magnetic field that gives you some non-zero flux, and then you scale it with a coupling constant. When the coupling constant is 0, of course, the flux will be 0, and the eigenvalues will be those of the Laplacian. And now, as you increase the coupling constant, of course, the flux will pass through consecutive integers 1, 2, 3, and so on. And each time it does, the eigenvalues will coincide with those of the Laplacian. So when that happens, I mean, are those values of the coupling constant, are they critical values in the sense that the eigenvalues attain the corresponding Laplace eigenvalues as maxima or minima, or is something else happening?
I understand your question, but I don't know how to answer you, but I understand very well your questions. Yes. I need to think. I cannot answer right away. It's not saying naive. Yes, it's.
I mean, I thought from some of the formulae that you had, you know, you had some formula involving minimum of distances, that at least for those special cases, the answer should
So sorry, minimum.
This is when you had the potential. What was it? Was it nu d theta or dt? I think you called it.
Yes.
And then I think you had some formulae for the eigenvalues. Or maybe I'm wrong.
No, some for. Sorry, I'm not so. So this is, for example, the potential for me.
Yes.
Then you say.
I thought somewhere I saw a formula. You had I thought I saw a formula. Maybe I wasn't.
For which? Sorry, I'm not understanding.
I thought there was a formula for the eigenvalues in this case.
For the state, yes, I have a formula for a simple case. Say, for example, here, for example, for the Steklov, but for the disk.
Right. Yeah, and so there, the fact that it's modulus really makes it look like it's a non-smooth dependence on the on the view, actually. Okay, that's interesting.
Yeah, there is a modulus here, yes, but it's some artificial. Actually, yes, I understand what. Yes, I understand what you say. Yes. Now I need to think. Maybe you can write to me, so I need to think more with more calm about that.
Okay.
Right.
Thanks.
Thank you.
Further questions for Luigi?
Can I ask a question?
Oh, please go ahead. Yes.
Yes. So you had your statement. Thank you for a nice talk, by the way. You have your statement for the Neumann boundary condition.
Yes.
Will you have a Faber-Krahn inequality in the right direction, so to say, for the Dirichlet condition?
Well, for the Dirichlet is trivial in the sense that among all bounded domains is the minimum is attained by the first eigenvalue of the Dirichlet Laplacian on the disk. In the sense when your pole moves to the boundary, you are going to the first Dirichlet eigenvalue on the domain, because when your pole moves to the boundary, you are moving towards the Laplacian eigenvalues. And the minimum is attained exactly in the ball when the pole is in the boundary or outside. That is for the first eigenvalue of the standard Laplacian. So it's trivial for the first Dirichlet eigenvalue. It's trivial. While for the second Dirichlet eigenvalue is again very. I tried to look at. I believe it is another open problem. It is not the union of the two balls without the pole. It's not clear. It's not clear what is for the second part. But the first one is the standard Laplacian, Dirichlet Laplacian, the first eigenvalue of the Dirichlet Laplacian on the disk, on the ball.
I have another question. If you start with a domain, functions which are compactly supported away from the Aharonov-Bohm flux, you will typically not get essentially self-adjoint operator, right? You will have several extensions.
Wait, sorry. So if you. No, sorry, I don't get your question. No, please tell me what. So
if you start with functions that are not really touching the Aharonov-Bohm singularity, so to say that you have a disk with Aharonov-Bohm inside in the middle, you get several different self-adjoint extensions. This has been studied by Johannes Brache and. In the full plane, it was by Adami and Tita and Dabrowski and Stovicek, I think. So my question was that if you look at some other self-adjoint extensions,
no, I don't.
Would this still hold, or is it something that's special with your self-adjoint extension, so to say?
Well, actually, I don't know, because I should need. Actually, this depends really on the behavior. It seems artificial, but it really depends on the behavior and the eigenfunction on the disk. So I should have a look on what the eigenfunction on the disk looks like. So really, I need to look at that in order to conjecture if it holds or not. I should check that. That is really what matters. The form. The shape of the eigenfunction on the disk, so that it was.
Yes, exactly. The different extensions. I mean, the functions in the domain, they satisfy some different type of asymptotic close to the singularity. So.
Yeah, yes, I need to see what they are. Yes, yes. I need to check, but that is the point. To look at the shape of the eigenfunction of the disk, and it should be enough. Okay.
Okay. Thanks again for a nice talk.
Thank you.
Are there any more questions for Luigi?
I have a question. Hi, Luigi. Thanks
Hi.
for the nice talk.
Thank you.
So have you tried to compute the derivative with respect to the domain, at least in the Euclidean case, or?
The shape derivative.
Yeah.
I computed the one for disks, only for disks, but it should be.
Okay, it's quite important.
No, not. I believe it can be done by standard. I don't believe it's really different from the Neumann one. Say,
okay.
At least the techniques, but I did for balls, but just for fun. But it's not really different from the Neumann, the standard Laplacian case.
And can you deduce some information from the derivative?
Well, for the derivative in the disk, we deduced some information which were essential, like on the behavior of the eigenfunction on the disk, but other stuff. But I used only for my purposes. For other things that I know you have in mind, I haven't checked actually.
Okay, thank you.
Any further questions, comments?
I may have a quick one if there is still time.
Please go ahead.
So thank you, Luigi, for the talk. I wanted to ask you something about the Neumann boundary conditions case. So it seems to me that you somehow reduced the problem to proving a reverse Faber-Krahn for this Schrödinger operator. So my question is, of course, in this situation, you're considering a precise potential, that is the one somehow associated with the Aharonov-Bohm pole. But what about like a more general potential? So
no, the reverse Faber-Krahn here holds for any potential which satisfies these three assumptions. If
I see.
It satisfies these three assumptions in any space dimension, it holds.
And do you think this is sort of sharp, or
no, because for example, for the ball, in the case of the ball, in the case of the sphere, with these three, we can get up to pi/3 domains containing a cap of pi/3. But doing by hands, we can do more. So these are somehow sufficient, but not necessary conditions.
All right. Thank you.
All right. If we don't have further questions, do we? Doesn't look like the case. So let's thank Luigi for the very nice talk. Very interesting. Thank you.
Thank you very much. Thank you again for the invitation.
Thank you. And yeah, and so see you all next week for Pier Domenico Lamberti's talk, again online. So thanks all.
Thank you. Bye-bye.